Welcome, everybody. Can everyone hear me okay? Awesome, that's great. So this is a code talk, so I just want to make sure everyone realizes this is not a dark room to hide and just look at slides. This is interactive. We're going to start off with some questions that we're going to ask, and we have a few slides to go through for sure, but the more questions you ask us, the more we'll get out of it, and I have a way to encourage that. I've got stickers. So ask a question, get a sticker. That's the way this is going to go today. So we'll get through a little bit of a setup here to set up the conversation. We're going to talk about performance, obviously. But after that, we want you to ask us questions, right? That's the idea behind today.
That's going to be more of a console talk than a COD talk, but
there you go.
Rename it. So.
We'll get there. But before we dive into it, I just want to get a sense of who's in the room today. Show of hands, if you ever looked at your application's performance, the metrics around your application performance and thought, you're not really sure why it's running as fast. It should be running faster than it is. All right, I see a few hands up. For those of you that didn't raise your hands, I'm going to say you're either incredibly lucky or optimistic, but we're going to figure out which one today. Okay, hands up again if you ever tried to optimize performance by throwing more compute at the problem. Maybe a bigger instance, more cores, more memory. Lots of hands up for that.
Thank you, that's why the stock is so high.
And then, last question.
You don't record that one?
Last question. How many of you have heard of terms like NUMA nodes, cache lines, CPU affinity, but honestly weren't quite sure exactly how that impacts your application performance? All right, see a few hands for that. Okay, I think you've all come to the right place. I think based on the show of hands, you're in the right place here. But there's a persistent myth in our industry that modern compilers and cloud infrastructure have abstracted away the need to really understand hardware. We can just write clean code, deploy it to the cloud, and magic happens. But here's the thing, and this is what we're going to explore today. The difference between code that runs and code that flies often comes down to understanding the hardware beneath these abstractions. So let me paint you a picture. Imagine you have two identical servers, running identical code, processing identical workloads, but one consistently performs 40% better than the other one. No visible errors, no obvious bottlenecks in your tools. What's going on? The answer might be as simple as which CPU cores your threads landed on, or how your data structures align with cache lines. So when you're pushing the limit of what's possible, when every millisecond of latency matters, when you're trying to squeeze every drop of performance out of your infrastructure budget, that's when understanding these low-level details transforms from interesting trivia into critical knowledge. Today, we're going to pull back the curtain and explore memory topology and explain why your RAM isn't just one big pool. We'll examine the art of hyperthreading and why sometimes using fewer cores gives you better performance. We'll talk about, and more importantly, we'll talk about how to actually measure performance in a way that gives you more than just pretty pictures. And most importantly, we're going to learn how to make informed decisions and when these optimizations matter and when they don't. My name is Seth Fox. I'm joined by Arthur Petit-Pierre. Let's dive in. So I want to talk for a second about how to read the EC2 instance portfolio. Over the years, we have lots of instances, lots of instance families to sort of dive into, but there is kind of a decoder ring, and that's the sticker you'll get. It's going to look a lot like this, but sort of break this down for folks so that we understand what we're looking at. So we have, I've highlighted three of I call them our workhorse instances, CMs and Rs. Those are compute optimized, memory optimized, and general purpose instances. And what does that mean exactly? It's basically a vCPU to RAM ratio. And you can see the ratios up there, and as you sort of move through those, the vCPU to RAM ratio doubles as you go up that stack. Now this decoder, we're going to decode a compute-based instance here, but it'll work across our instance families. So if we look at this, we've got a C8GN 2 extra large. So what does that mean? I've got a compute-based instance, right, because I know that I see the C. It's 8th generation, so you can see where it fits in the lineage of compute-based instances. And then there's a couple of options for this instance, G and N. The G tells us this is a Graviton instance, so it's got a Graviton processor in it. And N tells me this instance has some difference in networking, some specialized networking. So now we get into the number, the 2x large is going to tell us how many vCPUs there are. So everything doubles. We start with 1 is medium, 2 is large, 4 is extra large, 4, and then 2 extra large becomes 8. So now I know I've got 8 CPUs, and because of that, I've got 16 gigs of RAM because I know the ratio for those things. So when I break this down, this is an 8th generation compute-based instance with 8 vCPUs, 16 gigs of RAM, and the specialized networking is up to 50 gigs of networking. So while this is decoding at one compute-based instance, like I said, this will cover our entire instance portfolio as you're looking across that, and you can use that to break down different pieces as you're making those instance choices.
One last comment before you go to the next one. We mentioned in the table at the top left that CMNR or with the different amount of memory. There's a myth that we encounter extremely often that dates back to 5th gen, which is that the processors on the Cs might be faster than the other ones. The last time it was true was for Intel 5th gen AWS instances. Starting from Gen 6, we have the exact same processor on C, M, and Rs. So if you're using an M6i, you have the exact same processor on a C6i and the exact same processor on an R6i. Makes your life as someone analyzing performance much, much easier. It's also much, much easier when you're using things like Spot and you want to diversify. That's still the same processor. And as much as possible, we will try to keep that a real thing for the next generation. So that's definitely true for the 7th gen across the board. So on the Graviton side, a 7th gen Graviton-based instance, that's a Graviton 3, and that's the same one for C7G, M7G, and R7G. That's the exact same thing on the AMD side. That's the same Genoa-based processor on AMD 7th Gen. And we've done that again with Gen 8, and we will do that again with Gen 9. I cannot promise that it's going to be the same for Gen 15, but for as long as we can do that, we will try to do it. And we tend also to make that broader. So with the I instances, for example, we've been using the same processors as in CMNR. Yes? I'm not sure whether that thing is on. Give it a try. Yes, it's on.
Cool. So you have AMD, Intel, and Graviton, and even within Intel and AMD, you have multiple families and multiple, as I said, lineages. So even within different CPU brands, they are still the same performance?
No.
So
that would be
just
too simple.
That would be too simple.
So the processor is exactly the same within the same brand of processor. So C8i, C8i, M8i, and R8i, that's the same processor and the same performance profile.
Within the generation.
Within the generation. Now, if you move from an Intel to an AMD, they're going to be super different. If you move from an AMD to a Graviton, they will be super different. And I cannot tell you there's one that's going to be better at everything compared to the other. I can give you guidance. I can tell you that in general, a Graviton processor will be more cost-effective, but in some cases, an AMD processor will be more expensive, but will be faster. And there will be other combination with Intel. And there's never going, well, it's going to be hard to have an easy answer to that question, because they are optimized for different things, and so they behave differently. And you will have, and we will see that later, you will have cases where, you will have plenty of cores in the same memory domain on a Graviton-based instance, whereas AMD has done a totally different type of optimization, and you have clusters of 8 cores. It will have a different performance profile when you access the memory. It will have an impact on your applications.
So I know within vendors' server chips, they have different SKUs and they have different TDP and clock speeds. But you're saying that these EC2 VMs, like the underlying hardware, is just a uniform SKU across the board. So there's no, I know the lower core count tends to have higher boost frequency and that sort of thing. But going lower core count on these instance types will never yield higher performance in single-threaded applications versus higher, because the underlying hardware is uniform.
As usual, it won't be a straightforward answer, but yes, a VM is a slice of a big server. So when you run on an EC2 instance, what you get is a slice of the big server. Internally, by the way, we call those big servers droplets, because the cloud is made out of droplets. And so that big droplet is going to have as many cores as the biggest sizes in the family. So if I take the example of a C8G48XL, that's going to be a 2-socket server with 2 Graviton 4 processors, each having 96 cores. Now, if you take a C8G.large, that's a 2 vCPU instance, that's one slice of that 2-socket 192-core server. In a sense, no, it's not because you select small VMs that you will get a higher frequency, because they are taken as slices of a bigger one, and those bigger ones, they have all the exact same underlying processor.
Within a generation and for a specific vendor, those droplets are homogeneous across the entire?
Yes.
Okay.
Now, that being said, we do have, if you really care about super high frequency, we do have special instance types, like the R7IZ. They're usually postfixed by a Z, and those have been designed for high frequency, so usually above 4 gigahertz. We used to have M5ZN, that was one such instance. We had Z1D. They tend to be instances that we designed for things like EDA, where getting the highest possible single thread performance is very beneficial.
Cool. Go to the next slide.
So talking about type families and processors, so we started talking a little bit about that, but basically what we call the general purpose regroups 3 different types. The T, so the T, they are the burstable instances. So they are the only type with the flex type of instances in AWS to be overcommitted, meaning that on those ones, we run more VMs and we sell more vCPUs than there are actual physical cores. Great for costs, great when you have an application that has a limited performance requirement, but probably not good for anything where you really care about performance. M, we mentioned it, so those ones are not overcommitted. When I mean not overcommitted, it means that every time you get, let's say, a 2 vCPU based instance, we've carved for you 2 vCPU on that instance. And we do it the right way, meaning that those allocations are static. The VMs, they're not floating around. When you get allocated 2 cores, you stay on those 2 cores, so when the cache is warm, it's going to stay warm for you. We never allocate anything across the boundaries of a NUMA node, so you will never end up on an AMD instance with 4 cores on one CCX, 4 cores on another. It's always across the boundaries. So if you have a VM with 16 cores in 7th Gen AMD, that's going to span over 2 CCX, and we'll dig that a little bit later. Compute optimized, again, don't think that because the name says compute optimized, those processors are faster. It just means that if what you care the most about is having compute power and you don't care much about having a lot of memory, that's what you need, 2 gigabytes of memory per vCPU. Memory optimized, again, doesn't mean that the memory is faster. It just means that you get more. So on an R instance type, you get 8 gigabytes of memory per core. U, that can be much more than that. X, that's 16. Z, well, there are a few Z instances, but it happens that Z had 8 gigabyte of memory. Accelerated compute, that's where you will get GPUs, FPGAs, and various other types of accelerators that we have introduced. Storage optimized means that you get local disks that are physically inside the server and not the virtual disks that you have, things like EBS. And HPC optimized, those are very special instance types that are made out of the same hardware but have a special ring fencing mechanism for HPC application. Flex instances, you will see that some of the M and the OR instances exist as a flex version. That's exactly the same hardware as the normal class, except we overcommit them and we load balance them so that most of the time you will get 100% of the performance, but you can go down to 80% of the performance of the underlying hardware. Super convenient when you're not super critical on the performance side, very cheaper. But if you want perfect reproducibility on the performance side, then probably they're not for you.
Any questions on this? There's a lot here.
Are they similar to the T's? Is this the way you used to use?
They're better than the T's in the sense that you don't have that mechanism where you credit CPU cycles and then you consume it and then you reach a stage where you're out of credits and then we have that unlimited mode. It's a more steady type of utilization, so it's more predictable, let's say.
Because I've been thinking about using flex synthesis for things like the staging environment and development environment where like there's not a huge...
Yep.
Totally makes sense.
Staging's a great.
Yeah.
Staging's a great place for that.
Now, if you really want to evaluate the maximum throughput that you can get from an M, don't take the M flex. Sometimes you will get 100%, sometimes you will get only 80%. But for staging environment, when it's mostly functional tests that you're going to do on them, it doesn't change anything. And when you know that only getting 80% of the max is sufficient for you, that's also a great fit. And most of the time, you will get more than 80%.
Do they work with the same interface as like normal on-demand?
Exactly. Nothing changes. It's just like you name it whatever dash flex, and the biggest sizes are not available as flex.
Arthur back here.
Yep.
So on a T instance with unlimited credit, do I know when I'm being throttled and I'm not getting the full 100%? Is that visible in any way?
Yes, it is. But to be honest, nowadays don't use the T classes anymore. Like unless you really do things that are non-critical, use the flex. They're a much better proposition.
Got it. Thank you.
I guess kind of a similar question for the flex instances. Is there a way to know kind of where in that 80 to 100% your workloads are getting? Okay. So if you're being...
You have to trust us.
If you're being
a bottom,
throttled...
though, right? There is a bottom, though.
So what happens behind the scene is that we are load balancing those instances with transparent migration. So we have a pretty efficient mechanism to ensure that you're not all of a sudden in a droplet that is so hot that you're down to 60%. We just transparently migrate things.
Gotcha.
And transparent migration has been something that AWS has been shy to talk about. So we've been doing it since quite a long time, mostly for reliability purposes. It's now in the EC2 FAQ, but we were doing it long time before it was in the FAQ. We don't expose it to customers in the sense that you can't schedule the migration of one of your instances, but we use it a lot behind the scene, and it's a really reliable mechanism.
I mean, the way to think about it as an instance is a completely virtual construct, right? It doesn't live in a place, it lives in the cloud.
Okay, let's talk a little bit about what are the actual processors that are on those different instance type. And here I'm going to mostly focus on CMNR, and anyway, that's probably 90% of what you're using. So for those of you who are more familiar with the code names of the different vendors, we often get the question of, okay, what is behind your 5th gen, 6th gen, whatever. So Gen 5, and another important thing, when you're doing performance comparison, even though I would tell you, like, use the latest, because that would probably be the right thing to do. If you do comparison with different processor types, there's kind of a generation gap. A Graviton Gen 6, for example, would be comparable to an Intel or AMD Gen 5. And it's true across the board. So Gen 6, that's comparable to a Graviton Gen 7. Gen 7 Intel and AMD, that's comparable to a Graviton Gen 8. And, well, for the rest of the Gen 9, Graviton is not yet there, but that will come at some point. So Gen 5, on Intel and AMD, Intel, we had Skylake and Cascade Lake. That was a weird thing that hopefully we won't do anymore. We introduced it with Skylake, and then we did a silent refresh with Cascade Lake, and it had almost the same performance profile, but in some cases, the Cascade Lake was a little faster. So that was a little weird for customers. We've not done it again. Customer complained, and we listened. AMD Gen 5 was ROM, and on the Graviton side, Gen 6 was Graviton 2. One recommendation I would have: don't use those any longer unless you're using them through spot. The price-performance ratio of those instances is no longer worth it. So switch to things that are more recent than that, and you will get better performance. Gen 6 Intel and AMD is priced exactly the same way as Gen 5, and it's faster. Not extremely faster, but faster. So there's absolutely no good reason, unless there's no capacity available, to use Gen 5 on Intel or AMD, or to use a Graviton 2 on the Graviton side. Even Gen 6, compared to what we have released recently, I would say they start to be old. Okay, they're cheaper than Gen 7, but in terms of price-performance ratio, you would be better off using a Gen 7 or a Gen 8. So on the Intel side, that's an Ice Lake. On the AMD side, that's a Milan. And on the Graviton side, 7th Gen is Graviton 3. Now, more recent, Gen 7 on Intel is a Sapphire Rapids. Gen 7 on AMD is a Genoa, a great processor. And on Graviton, that's a Graviton 4. And then the latest that we have released a couple months ago, we have a Granite Rapid on the Intel side, and we have a Turin on the AMD side. And Graviton, well, it's easy to guess, and that will come. A couple trends that we have seen over the last years. The number of cores per socket is going up. And that's true across the board. You've seen that on Intel, you've seen that on AMD, you've seen that on Graviton. And that won't stop. That's going to be true for the next generation of the various instance type. The dollar per vCPU is also increasing. The manufacturing technology, the memory technology, all of that is more expensive. So the price on a per vCPU basis has gone up. That being said, the dollar per amount of performance has decreased because the performance has increased. So even though on a per vCPU basis it's more expensive, if your application actually benefits from the performance of the processor, you get a better value prop. The power consumption per unit of work has also decreased. So if you want to be a little bit less intensive from a power consumption standpoint and be a better planet citizen, you'd better use the latest generation of instances. They're a little bit better.
Does anybody have sustainability goals in an organization? Show of hands. Yeah, the Graviton and taking advantage of latest processors will help with a lot of that.
Another trend that we've seen, and we'll see how that will evolve, is that some of our processors are using simultaneous multi-threading, so the ability to use 2 or more thread of execution per physical core. Some of ours do not, and that has an impact on the performance and how you measure the performance, and we'll see that a little bit deeper later in the presentation. So a couple of things, well,
Why don't we
before
pause
we get
and see if
that,
there's questions? What questions? Where can we go next? Everyone's going to be quiet today. It's the first day. Everyone should be excited. Not tired yet. Here we go, down in front.
Okay, so a couple of things about the
Hang on, Arthur, right here.
virtualization
We got a
stack.
question right here.
Are all of the families of that we've been discussing available in Spot instances, and where does the Sapphire Rapid name come from?
So they were all available as Spot right from the beginning. So when we release Spot, the Spot market is enabled. But the question is not so much, are they technically available as Spot, as much as is the capacity sufficient for a healthy Spot market? Because when we release, and some of those things are very successful start from the release, and customers are massively moving over to the new generations, there might be very little capacity for Spot. So before you get a healthy Spot market, it usually takes a couple weeks, more realistically a couple months. Though I would say that in general, the very early adopters of new generations or the Spot customers who have, usually the Spot customers using Carpenter or the very early adopters. Because when you use an allocation mechanism with Carpenter saying, I want everything starting from generation X, the day we release, before any on-demand customer has started to use those instances, boom, you're using it. And the price is low and the performance is great. And then the on-demand customers start to switch, and then the Spot market kind of disappears for a couple of weeks until we launch enough capacity that you start to have a healthy Spot market. Now about your second question, the code names from Intel. I think that most of the code names are coming from rivers and lakes in the Washington state. That used to be true for sure. Nowadays, I don't know, because I don't remember whether there's a Sapphire Rapids anywhere in Washington. I moved, like I was in Seattle until 6 months ago, and I've never seen any Sapphire Rapids. So
Our processor name's a little bit more straightforward. Graviton 1, 2, 3, 4. Pretty easy to track, and you know where it came from. You had another question here?
Real quick, a reply to what you just said, but why is Graviton 2 generation 5?
Gosh.
Great question.
Because there was no Graviton when we released the first generation of EC2-based instances. And don't ask me why the first generation of Graviton-based instances was called A1. Because that was our first ARM processor. And maybe at that time we had the idea that we would call the next one A2. But we never did that. And we had A1, which was a porting vehicle. And then the next gen, we had C, M, and Rs that were C6G and M6G and R6G. Like, honestly, I would not want to be the one within the EC2 product management team having the responsibility to name the instances, because however you choose to do it, you'll screw up at some point.
And then my other question was, so you said as generations increase, the price per vCPU goes up, but the price per performance goes down. Is there any methodology for like evaluating whether you'll save money going to a new generation? Like if you're on a 8-core workload, you have to go down to 4 cores in order to decrease your price, right?
It depends. If your application is really running on a single instance, yes, that would be a problem. And there's the trick where if the performance goes up, because usually you have multiple parameters. It's not only the performance of the CPU, but it's also, okay, I might really need that amount of memory for my workload, and I also need that amount of network for my workload. So if network is really not the bottleneck, potentially you can go to, you're on a C, you can go to an M with half the number of cores. And maybe that's a sweet spot for your application. But more often than that, you might have a pool of servers, a pool of web servers that are serving a given workload. And you have your a certain number of requests that you have to serve coming from your customers, and it's fluctuating, and let's say that on average you're using 100 of those servers. Well, if you have one that is faster now, maybe on average you will be using 80 of them. So they're more expensive on a per instance basis, but you're using less of them. And it doesn't need to be, I need to be able to use half the size.
And don't worry, the idea is not to necessarily worry about the CPU load on your machines, worry about how much, what is the API request per second? What is the business measurement of that instance, right? The throughput of the instance, and if that you test it, right? If that goes up, then you're getting that price performance metric.
Now, if you have that single server, only one, and there's no way you can distribute that, then you're right. You get better performance, but you pay more.
So I've got a question about spot markets and like the health of them. At what point do you guys start tearing old server racks out? I run a lot of bioinformatics workloads. They need boxes and memory, but they don't really care about speed. I've got everything going back to like M4s. Is there a point where like there's a deprecation, stop using these, we're gonna start tearing them out?
So if you have things running on an M4, it's probably no longer running on M4 hardware. It's now running on Xenon Nitro, where we emulate our previous generation of virtualization system, and we make you believe that you're still running on an M4. And it
works.
It works, and if you're in a company where you had to validate that software with that specific piece of hardware, it still worked the same way, but on our side, it's probably no longer an M4. So we try as much as possible not to retire instances for customers who need them. So there are accounts where you can still launch an M2, but that's no longer a real M2. Now, from a price performance standpoint, don't run on anything that old because it makes absolutely no sense. From a price performance standpoint, there are other reasons to do it, but otherwise, yeah, I don't think we ever, well, we did, but for some specific instances, like old GPU instances where we can't emulate that and we could no longer maintain the hardware, and then we have retired those instances. But in general, we do our best to make them available for as long as we can.
Question back here.
I have one question. You mentioned about the price. For the latest instance type, the price would be lower, right? But one observation I made is when you're going with the reserved instances, I saw the older generation are much cheaper.
So I think what you mentioned is very, very true for RDS, where they change their pricing model for the RIs. I don't think I've seen that for EC2.
My experience, EC2 instance also I observed that.
Okay, it's possible. And we've been trying also to shift customers away from RIs and to saving plans. So what I mentioned in terms of pricing was applying specifically to on-demand. The way we've chosen to price those long-term commitment can be a little different.
So the second question, all the instance types are like one CPU, like memory and CPU are like strictly restricted, right? Is there any plan for AWS to, change? I can select the memory. CPU would be like, let's say 2, memory could be 4 or 8.
The same way as GCP does it, not that I would be aware.
Okay. Thank you.
But we offer more diversity also. It's the two ways to handle that problem. It's either you have a very small number, and then you make that, you can go custom, or you offer a lot of different combinations, and I believe that we cover a very broad number of possible combination. If there's something that is really, really missing, please let your account team know. We have a mechanism called PFRs, where we signal our teams that, well, there might be that thing that is missing, and if we feel like the demand for that is big enough, we might just do it.
My understanding is they may be moving away from that, by the way, so keep that in mind. I can't confirm this. They may be moving away from that choose your own instance configuration. It's a challenge to maintain for sure, right? But with over 950 instances, my hunch is you can find something that meets your needs within our existing portfolio.
At the end of the day, it's where we choose to expose the complexity. If we decide to expose that level of flexibility, it means that we add some complexity in the way we carve the instances on the physical hardware, because the physical hardware, well, is fixed. So it's really where we put the complexity. So far, we have chosen to put the complexity on you in some way, where we offer fixed sizes, we offer plenty of them, and you choose among those.
Good.
I have two questions.
Sure.
First one, you mentioned socket count. Is 2 the maximum?
No, on Intel-based X-class instances, you have 4 sockets. And on U-class that are very specific, you can't get them on demand, and they're mainly targeted for SAP, you can get up to 8 sockets.
The other question is around hyperthreading, and then you can, if you're going to talk about it, you can wait when you get there. But I've always wondered about Intel with hyperthreading turned on. Like for example, a simple example, 2 vCPU with Intel hyperthreading turned on, and AMD, which doesn't have hyperthreading turned on. Like,
So I'm going to talk specifically about that, and I will show you how to know.
Thanks.
Down here.
Hi. Without increasing the vCPUs and moving on from the previous generation to the new generation, how come the performance is getting better?
How is the performance better going from one gen to the next one?
Yeah.
Oh, that's because for all those vendors, they're improving the way those CPUs are designed. So there are plenty of ways you can do that. Gen over gen, there's usually bigger caches. And that's true. L1 has been pretty much fixed on the latest generations, but L2 has grown, L3 has grown. You have massive L3 cache on the latest generation of Intel and AMD. So that helps a lot when dealing with memory accesses and making your workloads usually faster. Another area that can be improved is changing the way the branch predictor is working. Same thing, plenty of applications that are super sensitive to how the CPU is able to predict what is the next set of branches that your code is going to go through. So it's a combination. The memory network has also improved, becoming more scalable. The memory latency has stayed pretty much at the same level, but the memory bandwidth has increased massively. On Gen 5 Intel, if I remember well, you had 4 memory channels. Latest generation has 8 memory channel. Latest generation of AMD-based instances has 12 memory channels. So by improving those different areas in the processor, you make them better and faster.
Let's say if my application has any performance issues, instead of just throwing more CPU into there, you want me to, it always helps or not?
Giving more CPU to an application is not always going to make it faster, because to benefit from more vCPUs, you need to have an application that has some level of parallelism. So if it is able to use multiple CPU, that's going to potentially make it faster up to a certain level. because you'll never or almost never have 100% of your application that can be parallelized. So there's probably part of that application that is still sequential, and you won't be able to accelerate that to the infinite. One other thing that I've forgot to mention about how processors have improved, they've also improved in the way that in how many instructions they can execute in parallel. Many people have a mental model of a processor of at every cycle you do one thing. But modern CPU, they do plenty of things at every cycle. They do memory loads and stores, they do addition, they do multiplication, and you can, on some processor, do up to 6 instructions per cycle. And some applications are built and optimized in a way where they can only extract a couple instructions per cycle from a given processor. And unless you significantly optimize them, they're actually underutilizing the CPU. So it's there's not a straightforward answer to your question. It requires more analysis and lower level optimization.
Thank you.
Okay, let's move on. One thing that, well, now most of our instances are using the latest generation of our virtualization stack, but when we moved from 4th to 5th gen, we've changed the way we do virtualization. We moved from Zen to Nitro. This definitely has an impact on the performance because we've offloaded a bunch of the virtualization primitives to dedicated hardware. So it has lowered the noise of the virtualization system. So even you could not really do the comparison because we never exposed the 2 virtualization systems on top of the same processor. But there was a significant gain when moving to the Nitro virtualization stack. It also reduced the noisy neighborhood effect that you could get from the previous system. There's almost no noisy neighborhood problems with Nitro, except at the memory bandwidth level. There's another thing that Nitro made possible, which is bare metal instances, because we've moved all the virtualization primitives outside of the instance, so everything with regards to network access, to EBS, and all of that is offloaded. So there's nothing that we really need to do at the hypervisor level from a security standpoint. So we can offer instances as a metal option where we remove the hypervisor and you get full control over the CPU. The drawback of that is we only offer them as full instances, so they do not come in small chunks. But in some cases, if you need to get full control over the processor, it's possible with the metal instances. From a performance standpoint, don't expect the metal instances for normal workloads to be faster. The level of performance penalty introduced by the Nitro hypervisor is extremely limited. There's a little bit of an impact for people having very, very strong requirement at the network level. So people doing high-frequency trading, for example, you'll see a difference. But for normal people doing normal web application databases, there's absolutely no point in going to metal, unless you need for other reasons to run your own virtualization system, but that becomes more of a functional requirement and not so much a performance requirement.
The hyperthreading question came up. Maybe we talk about it here.
There was a question?
The question before about hyperthreading, you were going to answer it. Is this the slide to talk about it?
Yeah. Oh, well, the title of the slides, by the way, is wrong. So you had a question about hyperthreading. I think I forgot who asked. Yeah. So that thing has changed quite a lot. So before we introduced Graviton, all our instances had hyperthreading enabled. So you had, for each physical core, you had 2 threads mapped to a physical core. Starting with Graviton, we introduced instances that were single-threaded. So each vCPU is mapped to a physical core. Starting with AMD Gen 7, AMD is also without hyperthreading. And that has a bunch of consequences on the performance side. So I can show you a quick demo on that. Okay, so what I'm going to do is here I'm connected on a C7i, so 7th gen Intel-based instances. If we look at what we have in /proc/CPU info, that's a C7i large. So that one exposes 2 vCPUs. And those vCPUs are actually threads of the same physical core. So I'm going to launch a quick OpenSSL speed test. Actually, I must have it here. And I'm going to do exactly the same on a Graviton-based instance. And that one also same size, so that's a large again, but this time we still have 2 vCPUs, but each of those vCPUs is a physical core. So we got a certain level of performance with that one. So if we look at what we were able to do in terms of signature per second, we were roughly 39,000. Now I'm going to do a second thing where I will do that, but this time with 2 execution threads. So OpenSSL has the ability to parallelize what it is doing. So it's actually using 2 processes to do that now, and we'll see what we will get from there. And so we get a slightly higher performance at 42,000 signature per second, but we don't double what we had. On the Graviton side, where we have 1 vCPU mapped to 1 physical core, if we do exactly the same, so first what we can observe is that in terms of signature per second, we were slightly slower with a single thread of execution. And now if we do it on 2 threads of execution, we have almost doubled. Not quite, but almost. And I don't want to use that test to say Graviton 4 is better than Intel in that case. What I want to illustrate here is that the SMT versus no SMT has an influence on performance. If you test your application at low levels of loads, what you'll see is actually 2 different types of design. Intel has big, beefy cores, and potentially they will give you extremely good latency at low levels of utilization. On the Graviton side, we have smaller cores, but we have more of them, allowing us to map 1 vCPU to 1 physical core. At low levels of loads, potentially we are not as fast. However, we scale higher. So 2 different designs leading to 2 different performance profile. I'm not saying use one versus the other. That's not the point. There are plenty of other metrics, and there are cases where the Intel processors will be faster, and there are cases where the Graviton processors will be faster. But keep that in mind when you're evaluating the performance of those instances. And the same would be true with AMD processors. AMD processors, it's a little different. We have chosen, because AMD had very high core count processor, we have chosen to expose them as non-SMT starting from Gen 7. They're more expensive on a per vCPU basis, but the performance you will extract if you're parallel enough and if you run them hot enough is going to be extremely good.
And I think that's a key point for this demo, is this was parallelized, right? Like the application can't be parallelized, it's not going to be able to take advantage. And that, going back to Arthur's point earlier, is that's a key distinction. If the application can take advantage of having those bigger, larger cores is important.
Yes.
question. So this information about hyperthreading, is that, I'm pretty sure if I...
So help everyone else hear you.
Yeah. So my question was, so this information about hyperthreading, for example, and probably CPU instructions and other things, yeah, I can probably find it on the internet. Probably there's a blog post from AWS saying this. Is that exposed on any APIs that could...
It's not exposed in APIs, but the processor tells you.
But then I'll have to launch an EC2 to check it.
Yes.
If I have a...
There are plenty of things that the APIs are not exposing. The API is not exposing the amount of L1 and L2 and L3 cache that you get on any instance.
Yeah,
the API is not exposing the NUMA topology. The API is not giving you, I don't know, the memory latency or the theoretical memory bandwidth. There's plenty of characteristic of a processor that the API is not giving you. Or other examples, each of those processors have options in their instruction set. So some generation of Intel processors have the ability to expose a 57-bit virtual address space. Not all of them, some of them. It's not in the EC2 API. If you launch an EC2 instance, you can check whether the operating system has been able to detect that specific feature. But there's way more to a processor than what we can really realistically expose in the API.
Because one of the possible use cases would be, so I have quite a few EKS clusters, for example. So if I could expose, I mean, I could create my own catalog. I could, do the homework and get exactly the instructions I care about and all that kind of stuff. But I could create node pools that would expose those instructions as labels, so I could schedule specific workloads onto a specific set of...
You have to run this once per processor, right? Right? So it's not like you're doing this indefinitely.
Per processor, per family, per...
Well, remember, if it's a C8, M8, R8, they're going to have the same processor in them, right? So it's not that...
Sure, but the 9 and the 10, I have to just do...
Well, and when we refresh, absolutely. And that's true of any time. If we launch something new, always test before you...
Well, I understand the request, and I get it. But there's a question of to which depth do we want to go there? So far, we have chosen to limit ourselves to exposing the frequency, exposing the CPU type, and once you launch the instances, you can get all those information because they are exposed to the operating system, but we don't make them available as an API.
If it's not an API, we own a blog post. So much.
We do have an internal discussion on whether we want to make it part of the documentation, which could be
This
a
even
way to
came
do
up
it.
yesterday, I think, right? So
The reality is that our team has that documentation for ourselves because we find it useful. So yes, we could expose that.
what else? Who else's questions? Here we go.
Can we go back to the presentation, please?
Right here, Arthur.
Oh, sorry.
With your demonstration, it was benchmarking on OpenSSL, and you compared a...
It's a terrible one.
Yeah,
don't have any conclusions from that.
No, you're comparing a 7th generation to an 8th generation Graviton.
That was on purpose.
Well, if you tried the 7th generation Graviton, I think you'd have probably lost significantly.
The two vCPU one, I would not. The one vCPU, that would be even slower. But
yes.
the two vCPU, no, I would still win that with Graviton 3.
Once upon a time, I tried to migrate load balancer to...
But that was another problem.
Yes, it was.
I know which one
CPU instructions.
you will be talking about. So the problem you probably have seen with an SSL load balancer was a Graviton 2 problem, where on Graviton 2, we made a mistake and we did not anticipate that it would have that kind of consequences. And the problem was that we did not anticipate that RSA would be that much slower on Graviton 2 compared to Intel-based instances. The reason behind that was that RSA uses a lot of 64-bit integer multiplications. And we had a single 64-bit integer multiplier on the Graviton 2 core. And when running a SSL connection, a TLS connection, at the session establishment, Graviton 2 was much slower. The AES part of an SSL session was much faster on Graviton 2 compared to Intel-based instances. So if you had long connections, nothing was visible, and Graviton was doing great. If you had short connections, like let's say a gateway for a bunch of IoT devices or a gateway for an observability system where you reestablish an SSL connection every time you send metrics, Graviton 2 was terrible. We fixed that with Graviton 3, adding one multiplication unit on the core, making Graviton 3 much faster. And then we also fixed partially, we mitigated that on Graviton 2 by optimizing RSA for Graviton 2. So within AWS LC, which is a crypto library from AWS, we have a much, much faster RSA implementation on Graviton 2.
Excellent answer.
That thing no longer exists, and Graviton 4 is doing great on crypto. So we've closed that gap. But that gap definitely existed at the beginning of the life of Graviton 2.
Great question. Who else? Where should we go next? We've got just under 5 minutes.
Okay, well, we have 5 minutes to talk about memory topology, Ben. So Earth isn't flat. And it's very visible on some AWS instances. So you know what that thing is? Well, actually, that's mentioned. And so that's the memory topology on a C7A. And what it exposes is that that processor is structured with groups of 8 cores. They are called CCX, compute core complex. And those 8 cores are sharing a slice of L3 cache and a connection to the memory die. So when you run on an AMD-based instance of that generation, your application won't see a flat topology. If you have an application thread that runs on that first block and accesses something in memory, and that part of the memory will stay warm in the cache, if you try to access the same part of the memory from the next CCX, the information won't be on the cache. And I've seen cases of customers moving from 4XLs, so that would be, 2XLs, so that would be one single slice, to 4XLs. Now you are spanning across 2 slices and seeing their application being slower. Because now they were across 2 memory domains, and if they were trying to access the memory from one domain where things have already been warmed up from the other domain, well, they had a cache miss, had to replenish the cache first, and that wasn't as fast as what they expected. And that one is on a 24XL. On a 48XL, you would have another level of non-uniformity, because you would have a second socket, and you would have an even greater distance between the cores on the first socket and the cores on the first socket and the memory associated to those 2 sockets. So when you deploy things on AWS, pay attention to that. The maximum sizes of our instances tend to be 2 sockets. So when going from, let's say, in that generation of instances, from 24 to 48, there are cases that may not be faster. You will get more core, you will get more memory, but if your application doesn't take into account the fact that the memory is no longer flat and uniform, you might have weird surprises. I had a customer a couple weeks ago who moved its database from a 24XL to a 48XL, and the P50 latency of his database doubled. Because now memory was spread across the 2 sockets. Okay, it had more memory, more vCPU, but the database on average was slower. Some requests were just the same speed. The overall throughput was higher, but the latency was definitely higher.
And this can also be an issue with Kubernetes, and someone was talking about using that before, right? If your containers land on different domains, right, now all of a sudden on different sockets, now the connectivity between them is slower than you might expect, right? And I see nodding heads. So that's something to definitely be aware of as you're looking at it. I know Kubernetes has got new feature of becoming NUMA aware, right? Something to look at as you're doing that. So just something that can become super important. These are some of those low-level differences that start to make a big difference in our.
Yeah, my recommendation, unless you know exactly what you're doing, would be avoid the 2 socket sizes on your Kubernetes cluster. Well, if you know what you're doing, then go do it. But otherwise, stay with the single socket. Again, well, we don't expose that in the API.
But even with multiple sockets, if you land on a multi-socket host, but you have a short, a small on-demand, would you impact it?
Yes.
All right, so
Does that advice apply as strongly to trying to keep it to a single complex size?
A lot less, because the difference in terms of latency and memory bandwidth between 2 CCX is much, much lower compared to between 2 sockets.
well, thank you, everybody. We are out of time. Please fill out your surveys. And for those of you that want a sticker but didn't ask a question, come see me. I'm happy to give them out.
Thank you.